Hello everyone, I would like to thank you for your time today. I'm Yuji Takiuchi from Toyohashi University of Technology. My presentation is about how to determine the equivalent seismic forces in single-layer reticulated shells. At the beginning, I'd like to show some brief background and aim of my presentation. Reticulated shells have been designed worldwide, including seismic-prone zones like Japan. In such countries, we have to consider not only dead load but also seismic forces in structural design. It is well known that determining uniquely the static seismic laws for reticulated shells is difficult because vertical responses occur when horizontal ground motions are input, and seismic response of the shell involves many vibrational modes. From this background, we investigated the applicability of the method of calculating the static seismic laws as in equation A to freeform reticulated shells as our previous study. This method is useful when the shell has two dominant vibrational modes. However, there are few studies about the relationship between shell configuration and the number of dominant vibration modes. Therefore, in this study, we are going to investigate the range of application of two-mode-based seismic laws. This slide shows the structural models. The shell geometries investigated in this study are spheres, cylinders, and freeform surfaces. Each shell is generated and analyzed by varying the parameters shown in the table. All members are assumed tubular member, and all connections are assumed rigid. The shape of the freeform shell is represented by nerve surface, and the heights of the control points are given randomly. From the preliminary analysis, shells with unrealistically large members are excluded. As a result, 214 analysis models are generated. Next, I'd like to explain the analysis procedure. First, the generated 200 shells are analyzed using natural vibration analysis and the response spectrum method. CQC method and two-mode SRSS method are used as the response spectrum method. More than 300 modes are used in CQC method, and the sum of the effective mass ratio is confirmed to be greater than 95% for all 200 shells. The relationship between CQC and SRSS is quantified by the coefficient of determination expressed as the square of R. As shown in the graphs, when the square of R is close to 1.0, it indicates that the CQC method and two-mode SRSS method correspond with good accuracy. In other words, the shell is dominated by two vibration modes. Next, I'd like to explain how to select the two vibrational modes. Among the model parameters shown in the equation on the right, we focused on strain energy ratio and the effective mass ratio. Hereafter, as shown in the screen, we named the vibrational modes E1 mode, E2 mode, R1 mode, R2 modes by focusing on the strain energy ratio and the effective mass ratio. As an example, the vibrational mode diagrams of a cylindrical shell are shown in the screen. The strain energy ratio of E1 mode is 80%, but the effective mass ratio is only 15%. On the other hand, the R1 mode has an effective mass ratio of 49%, but the strain energy ratio is 1% and the natural period is very short. This tendency was observed in many of shells. These graphs show the relationship between the coefficient of determination and the modal parameters of the E1 and E2 modes. The horizontal axis of these graphs is the sum of the strain energy ratios of the E1 and E2 modes. The vertical axis of the left graph is the sum of the effective mass ratios, and the vertical axis of the right graph is the sum of the bending strain energy ratios. Each plot shows the accuracy of the two-mode SRSS for a shell. The purple plot represents a group with the best accuracy of the two-mode evaluation. As you can see, there are many purple plots in the range of large strain energy ratios. On the other hand, the sum of the effective mass ratio is widely distributed and does not seem to correlate with the accuracy of the two-mode evaluation. If you look at the graph on the right, you can see that the spherical shell plots are concentrated in the range where the bending strain energy ratio is small. If you focus on the area of the red square, where there are many plots with good accuracy, 85% of the cylindrical shells and about 50% of the freeform shells are included in the range. On the other hand, there are no spherical shells for which two-mode evaluation is possible. In this slide, we focused on the E1 and E2 modes, but the same phenomenon was observed when we focused on the R1 and R2 modes. Therefore, we can conclude that it is important to focus on the E1 and E2 modes with large strain energy ratios. This slide shows the accuracies of the two-mode based seismic laws. Since we found that using E1 and E2 modes provide a good accuracy in two-mode SRSS, we use E1 and E2 modes to two-mode based seismic laws. Here, we focus on the group of shells contained in the red squares. These graphs show the estimation accuracy of the worst case in the shells contained in red squares. The center graph shows the actual force of the shell, and the right graph shows the bending moment. The horizontal axis is the stresses obtained from CQC, and the vertical axis is the response due to seismic laws. These graphs show that the analysis using two-mode based seismic laws is generally adequate to estimate the seismic response. Conclusions are as shown on the screen. Thank you for watching.